Good afternoon, ladies and gentlemen, and welcome to the new series of webinars from the metamaterials. So it's my great pleasure to introduce Corentin Coulais, who is a professor in the University of Amsterdam in Netherlands, who will be the first speaker of the new series for 2021-22. So Corentin, he's going to talk about all the robotics matter. So hopefully about waves to excite people from the wave community, but also about metamaterials, because we have quite a few guys in that field in the current list. So Corentin, you can start.
Yes. Yes. Thank you very much, Muammer, for the introduction, and thank you very much, Sebastian and Bogdan and Muammer, for the invitation to present here. I've been enjoying a lot the seminar series last year, and for now I have the task to kick off the new season, so that's exciting, and I hope it will continue even after we'll come back to post-pandemic world. So what I want to tell you about today is about odd robotic matter. In this research, what we do is we consider the physics of materials, of media, that have a non-conservative and asymmetric interaction. And we explore which sort of wave phenomena and properties we can exploit from those. And what you see here, and we do that by using robotics, or rather robotic media, which basically merge the world of materials, the symmetries, the concept of emergence that you're usually familiar with in materials, with the tunability, programmability of robotics. And so what you see here are two examples of phenomena we can actually observe. One is a unidirectionally amplified wave that turns into a soliton. And what you see is that actually a soliton that exists in a non-reciprocal media, so that's an active soliton, if you wish, and that can only propagate in one direction. And what you will see on the right video is actually a robotic medium that has a non-symmetric elastic tensor. And what we study is how it can deflect and control impact. And as you see that when an object impacts on it, it gets deflected and excites asymmetric Rayleigh wave that we will discuss later. But first, let me step back and maybe give you a little more detail about what I mean by the concept of odd matter. So odd matter, to me, is really are systems that have microscopic interactions that are asymmetric and non-conservative. And so, for example, if you consider an atomic chain, it will be a chain on which the electrons have a asymmetric hopping rate, so they can hop preferentially in one direction versus the other. As a result, you can describe those quantum mechanical system by a Hamiltonian, which is non-Hermitian, so in which energy is not conserved, and also that is not symmetrical. You have the same in, let's say, solids, so objects that are described by masses and springs. And these are springs that are non-symmetrical, so springs somehow that breaks Newton's third law, so springs that are stiffer in one direction than the other. So a bit as if, I was using a spring to push on you and you will feel more force than I would. And in those systems, so here you have Newton's law, where the acceleration is equal to the elastic forces, internal forces, and the matrix describing those internal forces is not symmetrical. And last example is actually viscoelastic fluids. So fluids that have a relationship between strain rate and stress. And in those media, you can have the viscous tensor or the elastic tensor that is not symmetrical. You can, for instance, think of odd viscosity in systems, for instance, that have a little torque density. So if your particles have a net torque, when they collide, they can exchange a torque, and this amount of torque density can, at the macroscopic scale, completely change the viscosity tensor and make it non-symmetrical. Okay. And so the first question, and this is actually a topic people are very interested in from many viewpoints, from quantum systems or active matter systems. What I want to focus on are the system in the center, mechanical systems, elastic systems, And I first want to get you through what happens. So first question I want to ask is, okay, assume you have such a material, assume you can make such a material, what is the emerging dynamics that you have? And so to do that, you can just go back to the simplest mechanical system you can think of, the one you have in the textbooks, and then just say, hey, let's take springs that are stiffer in one direction and in the other, okay? And if you do that, you can do many things. You can look at the vibrational spectrum, for instance. And what you find if you do that is the following. You find a spectrum that has imaginary frequencies. So if your asymmetry parameter here, epsilon, was 0, all the frequencies will have an imaginary part, which will be 0, so would be lying on the horizontal axis here. But that system, since you somehow can only create it by adding momentum, so you add local forces that do work, this work that those forces do is actually represented in this imaginary part of the frequency. You can also look at the modes in that chain, and the modes actually look like ordinary phonons they could have in a periodic chain. However, you can also look at the rate of those modes, or the imaginary part of those modes, and what you see when you do that is that you see that all the modes that have a positive imaginary part of the frequency, so the modes that are amplified, have actually a positive wave vector, which means that the forward traveling modes will be amplified, and the backward traveling modes have a negative imaginary part, so will be damped. And so it means that your medium can unidirectionally amplify in principle. Okay, but then an interesting question is, okay, what happens now if you don't have a periodic medium, but if you have an open chain? And what happens is there's a very drastic difference in the spectrum. Actually, all the modes now have a purely real frequency, and so they don't amplify, they don't damp anymore. But if you look at their shape, they are very, very different than the eigenmodes that you had in the periodic chain. They become all skewed. So they all become actually localized on the edge of the material. People actually refer that to as the non-Hermitian skin effect, because somehow all the modes seem to accumulate on the skin of your material. And there's a very strong difference between periodic and open chain, which is also a hallmark of this non-Hermitian skin effect. And the way to interpret this is, if your modes in the periodic chain are amplified when propagating forward, if you have an edge at some point, they're going to have to, they cannot keep on propagating when they hit the edge. They bounce back, right? And so at what you get at the end is that they bounce back, and but since they decay when they propagate backwards, they actually stay close and localized close to the edge, right? So that's really the essence of this object, and you have manifestations of this also in quantum systems. I'm going to discuss that later. But for now, you might ask me, okay, this is nice, this is an interesting model, there's maybe an interesting phenomenon, but how do you actually realize those springs, right? Because I told you, indeed, you need to add net momentum. And so how do we do that such that we can have asymmetric springs? Well, to do that, I'm going to use the concepts of robotic media. And so, as I said before, robotic media basically combine the concept of emergence and the concepts of robotic, and robotics is basically active control, right? And here I laid out a map on all sorts of active media, robotic media you can think of, and I like to maybe classify them in this with these two axes. On the horizontal axis, I want to think about the level of control that I put, and on the vertical axis, I want to think about the complexity of the behavior. And so this is maybe one of the simplest examples of robotic medium. This is colloid, so active matter. So you have a magnetic field that rotates, and this rotates the colloids. This injects a net torque, and as a result, you get those interesting chiral currents. And actually, this medium can be described by this odd viscosity that I mentioned before. And in a sense, this is very simple level of control, just an external magnetic field. And then physics, interactions do its job, and you have a quite relatively simple phenomenon, large fluctuations, large swarming, and that's it. On the other hand, you also have other types of robotic media, much more advanced. This is also an example where all those particles are actually tiny robots, And those robots basically obey or optimize some form of gradient descent algorithm such that they can self-assemble into a certain shape, right? And so this is actually a very complex behavior that you have, much like perhaps what you have in morphogenesis, a living object. But it's also very complex because you have to have, in particular, you need a feedback and you need global control. The system, every single robot needs to have knowledge of what globally all the assembly has to do. So it's a very strong, very strong information flow there. In between, you have perhaps intermediate cases where, for instance, you have let's say a minimum amount or you have still some level of control. For instance, here those grains oscillate and they are being told to change the phase of the oscillation such that they minimize the distance to an object. And then put together, they can actually locomote as a result of the interactions between those different particles. So this is the locomotion is an emergent phenomenon. But there is still feedback because the grains need to know how far they are from the source they have to go to. So there is still a global, let's say, a global objective that they have to be aware of. So there's still a flow of information between what they do and their targets, basically. And then if you also have examples in nature, and in nature, nature is very hard to beat because nature is very good at making complex machines with complex active control. But you have those examples of starfish embryos or even fire ants that cluster in some way, and they use all sorts of biochemical signals. I can't seem to be making the video work, but I guess you would see here fire ants moving around and here starfish crawling around. They have relatively complex behavior. I mean, living materials in general, they can move, they can do morphogenesis, they can die, but they have also fairly simple level of control, right? And so the question I want to ask there is, can we actually use robotic media and use it, pair it with the concept of odd materials to actually create robots or distributed robots that have a relatively minimal flow of information, but still achieve relatively complex behavior, right? And so that's what I want. That's what I want to do. And so to do that, I'm going to come back to maybe one of the essential building blocks of robotic media, which takes back to the work of Purcell, who was interested in actually swimming in low Reynolds environment, and he devised this very simple machine with 2 degrees of freedom, and he devised it because you need 2 degrees of freedom to be able to swim in a low Reynolds number environment, because that's the number of degrees of freedom that you need to break time reversal symmetry, right? And so this actually is a very minimal object that people use a lot in the context of robotic media or trying to understand living systems. That's a recent example here that I listed. And that's what I want to use to seed in this odd elasticity, odd response that I told you about. So this is our own Purcell particle, 3 linkages. That's 2 degrees of freedom, θ1, θ2. And if you straddle those linkages by a rubber band, what you have is the response individually. Each torque has a passive elastic torque that is proportional to the local deviation of the angle. Okay, and now if you now use active feedback, so control, you can actually create an asymmetry. For instance, you can ask with a little torque and sensor and microcontroller, what you can do is ask torque 1 to also depend on the deformation of the rotor 2, and torque 2 to also depend on the deformation of rotor 1, but then you can put, for instance, an asymmetry in this interaction, okay? And when you do that, what you see is that if I, for instance, open the left hinge, it will open the right hinge, but if I close the right hinge, you will open the left hinge and vice versa. So here you have it, you have your building block, right? If you're interested in a little more detail, this is how it's done in practice. You have basically a minimal robot that has a sensor, an actuator, a little microcontroller. They can communicate with its neighbor, right? So if we have this, it's good, because that's exactly the minimum building block that we need to have a dynamical matrix, so that relates forces and displacement that is not symmetrical. Right, and so the way we do that is we use active control and feedback, right? And so let's see. So now we have, these were the predictions from the very simple, let's say, textbook model. We should have waves that are amplified when you in the forward direction and attenuated in the backward direction. And indeed, well, this is just a demonstration. If you poke at the middle, you see that the wave will tend to be amplified towards the right and attenuated towards the left. So that's good. We have demonstrated that indeed you have unidirectionally amplified waves in that medium. Okay. So this is just a manifestation of a very generic phenomenon that occurs, across scale. So it was actually explored by Hatano Nelson at the end of the 90s and recently unearthed by some theorists working in quantum mechanical systems. And a lot of people have now realized, I think we were the first to actually see it, but we didn't even know that it was coming by the name Non-Hermitian skin effect. But since then, people have done this in electric circuits, in quantum walks, actually optical fibers, optical circuits. And actually, I think there was a recent talk by Professor Ngeta recently, also in the seminar series, where he discussed, I think, a related effect on diffusion. So you have a diffusion that is also unidirectional. Okay, so that's nice. It's a new phenomenon that's purely, coming from the fact your interactions are odd, non-conservative and asymmetric. But can we do something with it? What are the potential applications? That's the first question I'm going to try to address. And the second question is more fundamental question: is what is the interplay of this, let's say, non-Hermitian skin effect, this unidirectional amplification, with nonlinearities as well as topology? Okay. So the first application you can think of is actually quite straightforward. You can just make unidirectional amplifiers, right? And this is actually what we've shown, that using that concept, if the bandwidth of your control system is larger than the bandwidth of the waves you're interested in, actually you can be infinitely broadband. And so here we see that you have 50 decibel difference between the forward and the backward transmission in that system. Recently, some people in Missouri, the group of Young, I think, did that also on vibrating plates using a similar concept of active feedback. And some people also are interested in how you can use this for sensing. And you can actually leverage that skin effect to actually amplify the signal more than the noise. And that's what this group here in Chicago did recently. And also, for instance, what you can also do with optical fibers, you can also do that with light, and you can channel light and amplify it in only the one direction. And that's what people are, I think, potentially interested in for waveguiding and sensing as well. Right? So this is one potential application you can think of, unidirectional amplification. The other one that I want to discuss at length in this presentation is actually you can also do that to do robotics. And so this is a work in collaboration between Martin Brodin-Bourget, who's now a CNRS research scientist in Marseille, together with Jonas Venstra, who's a PhD student in my group, and Colin Scheibner and Vincenzo Vitelli from Chicago. And what we've done here is we've taken those odd materials and we've shown that actually you can use those waves, those skin waves, if you wish, to actually create very basic robotic functionalities, so locomotion and impact control. And so I'm going to showcase a few examples here. You have a hexagon that can climb up a ramp because of the way it hosts. You have a ring that you can launch against the wall and the impact gets deflected. Or as I showed before, you can also make a robot odd medium itself and test its response to impact. Right? And in all these examples, there's interesting nonlinear dynamics, interesting wave phenomena, and interesting, let's say, large deformation, large elasticity. But what you have to do is you have to revise what you know from the textbooks by taking into account this odd parameter that we now have, the fact that our tensor or matrix are not symmetrical anymore. And so the first thing that we also do in that system is we also look at what happens when you have nonlinearities. And so in any kind of system, you always have nonlinearities. They could be geometric or due from the dissipation or due from the gain. Here in this system, what happens is that if you crank up the gain large enough to overcome dissipation, at some point you're going to hit an instability. You're going to have some form of a bifurcation, in that case a Hopf bifurcation, and then you end up having a limit cycle. It's very, very traditional let's say nonlinear dynamics. Except here, this work cycle is controlled by actually this asymmetry that we can see in that we can control. And so that and we can use this robotic building block, this per cell particle, as a way to construct actually materials. And so that's maybe the first thing I can show you. If you can, for instance, make up an hexagon, you can let it float. So actually, for the record, we put now those robots on the air table that is friction free, and so the object can freely over around. And you see that indeed the object actually self-oscillates between these two shear modes. So it actually has two shear deformations here, and it can oscillate forever between those two shear modes. If you can also play, and that's what Jonas has done. You can also add more units, and then you get different types of limit limit cycle, not necessarily between two shear modes, but between the shear modes, but between more complex deformation patterns. And the question I want to ask here is, okay, now we have those deterministic work cycle that can emerge as an interplay between nonlinearity and this skin effect. How do those couple to the environment, and can I use that to make very basic robotic functionalities? So this is maybe one example. I showed you before, I show it again. I cannot get tired of seeing that movie. And what you see that indeed the object self-oscillates, it oscillates between those two shear modes that you have, and it's able, as a result of this, to actually locomote on a complex surface. And you can also just look at its impact properties, and that's what happens here. So we have 3 different values of the gain, 3 different values of the asymmetry, and you see that when you have no gain, you actually bounce back as you would, but normally for a passive object. But as you, if you actually put some gain, you see that you tend to bounce back faster with a spin and also a deflection. So you have created additional rotational and linear, angular and linear momentum. And so where does it come from? Let me replay that movie, but now I'm going to actually zoom in a bit more on, I'm going to decompose the dynamics of that object and also decompose its deformation onto its 2 shear modes. And what you see is that, okay, we impact it, it flattens, then it deforms, and then you see some wave that tends to be amplified. And this actually, this is for the other value of the gain, so it's going to deflect towards the left. Again, it deflects, and then you see the wave that tends to propagate counterclockwise. And if you track the shear mode, you see actually you start to see a cycle pretty much that starts to be saturated by nonlinearity, so pretty much similar to the work cycle I was describing in here. So what we see here is that the wave, you impact, you trigger the wave is amplified in one direction. As a result of this, it gives an asymmetric shape, and when it does so, it also creates a non-symmetrical reaction for us. And since it does create a non-symmetrical reaction for us, its impact gets deflected and amplified. Okay. You can actually dig a bit further. So what you can do is look at the amount of momentum that is transferred in the internal dynamics of the object. And the colored dots here are the experimental data. So you see that here we tend to propagate waves clockwise, and here we have counterclockwise, and this is just a quantification of how much momentum is actually propagating in one way versus the other. And so we clearly see that there is this non-Hermitian skin wave I was telling you about. And so can we try to rationalize that? So yes, we can. So you can actually, even though it's only 12 units, this ring, you can actually construct a continuum limit and that describes its object. And it's in this continuum limit, I didn't have the equation there, but you also have a term that breaks the left-right symmetry, the odd term. As a result, that wave here will be amplified in one direction, right? What you can do is, if you look at a specific wavelength, you can actually predict the flow of momentum that this wave will have. and that's actually this black line here. So actually we can, with this very simple continuum model in 1D, at the linear level, we can predict how much momentum, and see that it fits quite well the experiments here. We can also take a step further. So this is the data of the momentum transfer. So you see here that this is the lateral momentum and the vertical momentum. And you see that here you have some px, which means the object is deflected towards the right. And here the object is deflected towards the left. And here you have more py, so you have more vertical momentum, which means the object actually bounces back faster than it would in the passive case. You even have cases where you have if you sum the velocity, so if you look at the restitution coefficient, you will have actually a restitution coefficient more than 1. So it would amplify really you would really come out faster than you come in. Can we rationalize that with this basic model? And again, yes, we can. We can use the fact that actually this fiber here, odd fiber, is upon impact excited on the second mode, and you can predict how much it moves during the duration of the impact. And actually, you can think of it as really a piece of elastic material that has this non-symmetrical tensor, which means that has this coupling between the compression and the shear. And you can, with a very simple textbook model, you can really predict its momentum, the momentum it has gained during the impact. And these are the black lines here. So that means that we can really, quantitatively predict the internal dynamics on the left and let's say the impact property of the object. And so that's, I think, quite unique in the field of robotic media, because usually in robotic media, people don't really do this kind of continuum modeling and predictive descriptions of their interactions with the environment. Okay. We can also, of course, test what happens for the wall. So this is, we crank up our, let's say, engineering faculties to create an object that has dozens of those robots. So here 120. And we can make a wall, right? And then we can test the impact property of that wall. And here again, I'm going to play in slow motion what happens during the impact. And what you will see is that for a certain value of the gain, you have an impactor. You seem to trigger some asymmetric deformation, though some wave also seems to be actually asymmetric. If you look at the deformation in the shear deformation, you also see like a cycle in there. Now we're going to look at what happens for the other part, with the other sign of the gain. And you will see the exact same thing. You impact, you first shear in one direction, then you have some asymmetric deformations, you shear in the other direction, and then you have some wave here that comes back, right? And as a result, the object is also deflected. Okay. Okay, that's nice. Can we also use here continuum mechanics to predict what happens? The answer is yes. You can assume that you have a piece of homogeneous elastic material that has a non-symmetrical tensor. If you look at the really classical example of a point force, you actually see that the deformation here are not symmetrical. If you look at Rayleigh waves, you can actually solve for Rayleigh waves with asymmetry. You also see that you have asymmetric Rayleigh waves that tend to localize on one side. And if we now play again the reconstruction of the experiment, what we see is that indeed here we see asymmetry in the deformation pretty much. And at the end, after the bounce, we see also more oscillations towards one side. And you can quantify that. For instance, you can look at where the wave is localized in theory, in experiment, and these are qualitatively similar. Okay. All right, cool. So in short, we can really take those odd robotic media, and really give them new functionalities, meaning basic robotic functionalities, maybe a basic way of interacting with the environment, and still at the same time keep some predictive leverage about what they do and how they do that. And I think that's quite unique. Now, I showed you that there were some non-linearities there, and for some examples, for sometimes when you have some small degree of freedom, you have the emergence of some of some patterns of work cycle, but it seems to be depending on exactly the size of the system or what we do at the beginning, the initial conditions. So here, I want to really try to dig a bit deeper to understand the emergence of the stable nonlinear excitations. So the balance between this amplification of the skin waves and I said the nonlinearity that tends to saturate them. And so if you do that with a system where your nonlinearities are not stabilizing, what you will see is that the system will just tend to blow up and break. But if you control your nonlinearity very well, then in some instances, for very specific initial conditions, what you can have is actually a very stable localized wave that tends to propagate at a constant speed. And that looks a lot like what you know from soliton physics, right? So that's what you see here. The wave propagates for quite a long time. Sometimes it blows up, sometimes it propagates longer than you care to wait. And so the question is, can we explain that? If you look a bit more, this is a reconstruction of the experiment. What you see is that this is the wave traveling around. This is actually the data, the blue curve, and the green curve is the envelope. And what you see is that the envelope in the reference frame, what you see is that the envelope seems to be relatively stable. And there's a chiral wave below that envelope that seems to be modulating in time, but the envelope seems quite stable. So it looks a lot like what we know from solitons. If you look at the regime of existence of such objects, well, it's quite narrow. So you only can observe, actually it was quite hard. You only can observe it for a narrow range of initial conditions and non-reciprocity. So we would like to understand why, right? So to do this, what we do is we actually write the equation that describes the mechanical system, and we perform an amplitude equation. And then what we find is that actually we can write this in terms of a nonlinear Schrödinger equation, the normal one, but on top of this, you have a non-reciprocal term here. And this non-reciprocal term is the one that breaks the left-right symmetry. And the term proportional to it is actually a term that has a gain minus loss, right? So what it means is that this is actually it's not a physical frame, it's a frame that has been transformed because this comes from solvability conditions. But actually what you find is that when gain exactly balance loss, you can actually have a real soliton that is described by this wave. But when you have a little bit of loss, then we want to know what happens, right? And this is actually described in this graph here, where I plot the amplitude of the soliton as a function, or the velocity of the soliton versus amplitude. And what we see is three regimes. We see a regime here where the soliton dies. So if your amplitude is too small, the soliton will die. If your initial velocity of the soliton is somehow too big, then your soliton blows up. And then you have different regimes where actually the soliton is never quite stable, but there's a regime where it can live for a long time. So it first tends to actually decelerate and then reaccelerate. Also, its amplitude tends to go down and then go up. But you see this blue region here can take a while. So that's actually even if you don't have an exact balance between gain and loss, you can, for specific values of this epsilon and for specific values of initial condition, you can land in a system that actually behave quite as if, or is quasi-stable, if you wish. So this is interesting because somehow it extends the regime of validity of these solitons here. We're still busy trying to understand exactly how this maps out to the experiment, but that's basically the essence. How much am I with time, Bogdan?
You still have 20 minutes?
Yeah, including questions, or can I have the 20 minutes? And
take your time.
All right.
Whatever you need to take.
All right. Okay. So, so now I discussed what happens in a specific instance when we have nonlinearities. Now in the time that I have left, I want to discuss about the role of topology. Okay. And so for this, I'm going to come back to the basics, to what I showed you before in this very simple model. Oh, and I realize this is flipped. So this is what we had for this non-Hermitian skin effect. We have some waves that are amplified when their wave vector is positive, and if you have an open system, they tend to accumulate on one side. Okay. So now it's interesting to ask what happens with topology, because there's an argument in the literature where people argue that actually the side on which you localize the wave can be related to the, how you circle around, how this spectrum here circle around zero, or around the eigenvalues. If you cycle clockwise or anti-clockwise, you will localize the wave on the right, and if you cycle in the other direction, you will localize the wave on the left. And so we want to explore here what happens a bit more, and whether if indeed this is a solid connection with topology, or if it's just an observation. So to do that, we actually create the same system, but then we just use next nearest neighbors. Actually, that was something that was explored by Rosa and Rudzene also recently. And then what we see is that the spectrum actually changes. Now it's no longer like a rugby ball. It becomes some kind of fish or 8 sign. We actually wind in one direction and wind in the other. So this is actually interesting, because then if this topology argument is correct, we have actually two distinct signs of winding of this spectrum. And so in principle, we have two opposite signs of this topological invariant you can think of defining. Okay. I like also to think about qualitative picture. For instance, if your wave vector here is between 0 and a certain wave vector, it means that your wave that have a relatively small wave vector, so long wavelength, will be localized, will be amplified when they travel to the right. While here it's the opposite. The wave that have a negative wave vector, but then more negative than a certain critical value, will be amplified towards the left. So which means that the waves that have a frequency that is or that have a low wavelength would be accumulating on the right, and the waves that have a large wavelength will be accumulated on the left. And so indeed, if you look at the spectrum, it's true. Now not only you have waves that all massively accumulate on one part of the skin, but you separate your wave. So somehow you have made some kind of filter where you have selected all the wave below a certain frequency to accumulate on the skin that is on the right, and all the waves that have a frequency above a certain frequency will accumulate on the left, right? So that's kind of interesting. We can actually probe that in our system here. And actually, I think we're the first to have done that. It's not so easy, but you see that indeed, if you look at if you excite from the middle, and if you look at where the energy is as a function of when you crank up frequency, you see that here you tend to be localized on the left, and here you tend to be localized on the right. So that's a potentially interesting way to make not only a unidirectional amplifier, but that's a let's say bidirectional amplifier that depends on the frequency you input. So an interesting sort of device. And also it can ask the question, okay, is there some form of bulk edge correspondence? So if I wind around, if I wind around these values here, I will wind counterclockwise in this part and clockwise in this part. So in principle, this is enough to predict where my waves will be, but somehow it's a weak form of invariance, because you need still to know what are the red eigenvalues in there. And so that's a bit what also motivated us to look at stronger form of bulk edge invariance. And for this, you need here you see that you have one branch. So actually, it doesn't take anything. You don't require to close any band gap to actually go from this pattern to the single pattern that doesn't wind twice or differently, right? If you want to have topologically distinct winding, what you need is in fact 2 branches. And this, I think, in fact, was proposed by a group in MIT a couple of years ago. Where here what they have is two branches, the yellow and the blue. And then what you have is that you have two scenarios, either when the branches are encycling each other or when they are winding separately. And so what we have done in this work is to adjust our system and do it with two bends so as to have this topology and explore its consequences. And so that's what we did here. And to do that, we base ourselves on the mapping between this topological quantum mechanical system and this mechanical invariant. And the only thing we did was to make it non-reciprocal odd in a way by just adding, as I said before, here it's corresponding to electrons that have more chances to hop in one way than in the other, or springs that are stronger in one way than in the other. If you look at your Hamiltonian, that's what you have. You have a non-Hermitian Hamiltonian here. You see that these two off-diagonal terms are not equal to each other's complex conjugate. Okay. So if you solve this, that's indeed what you see. You see that for some range of parameters, your two branches are not winding, and for some other range of parameters, your two branches are winding. And so you have a transition between them winding and then not winding. And somehow we also always find that there's always a mode that is locked in the middle here by virtue of its topology. And so when we do that, what we find is that when you're not winding, the mode is localized on the right of the chain, and that's what you see here. And then it's winding, somehow then the skin effect takes over, dominates over that mode, and will push it on the other side. And this will happen precisely when the branch starts to merge and wind around one another. So this is interesting because then that means that you actually don't need to look at the finite size system to predict where the modes will be. So that's an interesting form of tuning or control or designing, let's say, motion or vibrations in these objects, right? And so you can do that experimentally. You can actually look at the spectrum by doing very simple experiment where you just let the system relax and measure its damping rate or amplification rate and oscillation frequencies. And you see indeed that you have two different types of routes where you go from non-winding to winding loops, winding spectra. And you can also measure the response by just moving the object in the middle and see whether it moves more on the left or on the right. So here you see you move more on one side, and here you see you move more on the other side. Here on the bottom, you'll have change, and you see more motion on the bottom left, on the left. Okay. You can do that for all the range of parameters, and you see that you can measure this winding number experimentally, and you see that when this winding number jumps, it's indeed the location at which your mode changes side. And this is interesting because I think no one really, I mean, in this community, people don't really manage to measure winding numbers directly. And here, because it's desktop scale, we can actually do that. So that's nice. And so, and there's here an interesting interplay between this skin effect and topology. So although the non-Hermitian skin effect is itself non-topological, you can actually, it seems to be, topology seems to be quite robust and affected in some strange way by this skin effect. So I want to conclude now by coming back to this slide. So I said, hey, we want to see whether this concept of odd materials can help us also design robotic media. And in a way, I want to claim that indeed it's relatively simple in the sense that here the information flow is quite local. I don't need, like those grains, I don't need global knowledge or global optimization procedure with compared to a global quantity. Everything is local. I just need robotics here to actually break this local symmetry, and that's it. And I can achieve quite complex behavior, for instance, locomotion and impact control. So in a way, I think this odd media and pairing with robotic media is an interesting combination to make basically resilient, adaptable robots that mimic, let's say, living organisms, and also allow us to probe interesting, let's say, non-Hermitian wave phenomena that you can have in odd materials, not only in mechanics. Interestingly, there's also a recent paper I was involved in where there's even less control and where you can use symmetry breaking to actually achieve nonlinear cycles as a function of symmetry breaking instability. There's a collaboration with a team in Paris led by Olivier Dauchot. And this could be a route to actually further simplify, further scale down, further scale up those robotic media by even taking away or trying to offload the active control to the material instead of keeping it in the Arduinos. Yeah. So to conclude, there's a lot of fun you can have with other robotic media. You basically engineer non-symmetrical tensors, non-symmetrical dynamical matrices, and you can explore this non-Hermitian skin effect, what you can do with it for unidirectional amplification and simple robotic functionalities. I think I'm done, so thank you.
Thank you very much, Corentin, for this night's talk. So now we have some time for questions. So just raise your hand, take the microphone and just start speaking. Or in the worst case, you can just ask the question in the chat. So just feel free to interact with Corentin.